To solve a system of equations in two variables, we will consider two algebraic methods, the substitution method and the addition method. It will not matter which method you use, but oftentimes it's easier to use one method over the other. My decision as to which algebraic method to use will depend on how the equations in the system are arranged. We'll discuss this as we go through this section and the next. Keep in mind that we are solving a system. Therefore, the two equations must be worked with together. As for the substitution method, we are going to substitute one equation into the other. In order to do this, one equation, either one, must be solved for a variable. The first step gets the equation you will substitute in prepared in order to do this. You will solve either equation for either variable. The substitution method is generally my choice of our two algebraic methods if I don't have to do step one. With step two, I'm taking the results of step one and substituting this equation into the other equation. After step two, you now have an equation in just one variable. And you can solve this for half of your ordered pair solution. In step two, you're finding the other half of your ordered pair solution. When we have a unique ordered pair solution, we will have a way to check, and we will want to take advantage of this check. Here's our first system. Notice how the second equation is already solved for y. That means I don't have to do step one, which makes the substitution method the fastest algebraic method of the two. Equation 2 says y equals x minus 5. Now understand that the equal sign, y is x minus 5, means that at any time I can replace y with x minus 5. So I substitute into the other equation, and what we find is that we have an equation in terms of one variable. And we go on to solve this linear equation. Because we ended up with x equals negative 5, we definitely have case 1, which means we have a unique ordered pair solution. We know the x coordinate, we just need to find the y coordinate. Go back to the original system and ask yourself which equation would be the easiest one for you to find that y coordinate. And of course, it's the second equation. You can use either equation, but we want to go with the one that requires the least amount of work on our part. So substituting negative 5 in for x, we find the y coordinate of our ordered pair solution to be negative 10. There's always a way to check. Recall, this is the one point that is common to both of the lines. Therefore, it is the only ordered pair that will check into both. So if you take the time to check this ordered pair into both equations and you find that it checks, in other words, you get the same number on either side after substituting in, then you definitely have the correct answer. Here's our second example. Again, with the substitution method, you solve either equation for x or y. I think the easiest thing to do is to solve the second equation for y. I always take the path of least resistance. Now we're ready to substitute this equation into the first for the y variable. In this slide shows that substitution. Now something different happened here. We expected to be able to solve for the x variable, but instead both variables have dropped out. On top of the variables being gone, we have a false statement. The purpose of this slide is to show us what the variable dropping out with a false statement means to us. And what I've done here is I've solved both of the equations for y. Now that they are solved for y, we can see, think in terms of lines, that the slopes are the same. And if we think of this system graphically, we have parallel lines, which means these lines will not intersect, and therefore there's no solution to the system. Therefore, our response to variable dropping out with a false statement is no solution. Let's move on to another system. Look closely at both equations. The first equation has a common factor of 2, while the second has a common factor of 5. Let's start by reducing each of these equations. Sometimes we're able to arrive at the solution to the system if we begin this way. Now check this out. After we reduce the equations, we see that they are identical. They were disguised very well, weren't they? We know what our solution is because the lines are the same, so the points on one will be points on the other. There are infinitely many ordered pair solutions. Let's take a look at what happens if we finish algebraically, just in case we end up going that route. So using the substitution, I'm solving the second equation for x. I will then substitute this in to the first equation. The result is the variable drops out, but this time we are left with a true statement. When the true statement results, you had the same equations to begin with. That means your solution is an infinite number of ordered pairs that would be on the line. Here's another example. Again, solve either equation for any variable. It is obviously easiest to solve the first equation for x. We then substitute this into the second equation for x. After doing so, we will have an equation in terms of one variable. We go on to solve this equation. Here we're solving this equation, and now because the variable did not drop out, we definitely have case one where we have a unique ordered pair solution. We have half of our ordered pair solution. We go back to the original system to find the x coordinate. Going back to the equation that was rearranged in the first step gives us the other half directly and fairly easily. And again, recall that if we plug this back into both equations of the original system, and they check, we have the correct answer. The ordered pair does check, so no doubt this is the correct answer. This slide summarizes the three cases that we can have. The right column of the table displays what we will see when we solve algebraically. And this last slide restates the two special cases, the cases where variables drop out. Remember, when that happens, variables drop out, you have a special case. If the resulting statement is false, no solution; true, infinitely many.